Good morning, Miss Bergonia, and to everyone. We are the Wonder Pets group from class Group 1 and Group 5, and we are here to present Unit 3 of the Fundamentals of Surveying. So here is the overview of our report. True and magnetic meridians, interior and deflection angles, which will be reported by Chan Dion Joseph. Bearings and Azimuth, which will be reported by Genabe Eisha Rose. Types of compasses and uses, and common errors and mistakes in compass work, which will be reported by Padilla Nichole. We will begin with true and magnetic meridian. Meridians is a fixed reference line or direction which lies in a vertical plane that passes through a fixed point of reference and through the observer's position. These imaginary lines on the Earth extend from north to south pole. It is a north-south reference line, a great circle, through the geographical poles of the Earth. The term usually refers to the upper branch, i.e., that half from pole to pole which passes through a given place, the other half being called the lower branch. There are four types of meridian, which are true meridian, magnetic meridian, grid meridian, and assumed meridian. First, we have true meridian, or also known as the astronomic or geographic meridian. It is a plane that passes through the true north and true south poles at the place of observation. The direction from any point along a meridian towards the north pole of the Earth is defined as true north. True south is also defined in a similar manner. Second, we have the magnetic meridian. It is a fixed line of reference in which line is parallel with the magnetic lines of force of the Earth. When the magnetic needle is suspended freely and balanced properly, it indicates a direction held at the observer's position. True meridian passes through the center of the north and south poles, but it is not necessarily in the case of magnetic meridians. Third, we have the grid meridian, which is a line that is parallel to the central meridian of a system of plane rectangular coordinates, an arbitrary set of straight lines constructed parallel to the 180 degrees and 0 degree meridians. We have to assume that all measurements are projected to a horizontal plane and that all meridians are parallel straight lines. The fourth type is the assumed meridian, which is an arbitrary direction assigned to some line in the survey from which all other lines are referenced. This could be a line between two property monuments, the center line of a tangent piece of roadway, or even the line between 2 points set for that purpose. The important point to remember about assumed meridians is that they have no relationship to any other meridian, and thus the survey cannot be readily related to other surveys. Next, we have magnetic declination and local attraction. Magnetic declination is the horizontal angle and direction in which the needle of a compass from the true meridian at any particular locality. It means that it is the angle between the magnetic north and the true north. See on the figure below. Next, we have the local attraction. It is when the magnetic needle is sometimes disturbed from its normal position under the influence of external attractive forces. It is due to the influence of other magnetic objects at a locality, such as wires carrying electrical current, rails, iron structures, and etc. So we'll be talking about interior and deflection angles. First, we have the interior angles, which are angles formed between two sides of a closed traverse within a triangle or polygon. A check can be made since the sum of all angles in any polygon must be equal. As you can see on the image below, we have a pentagon. And now, for us to find the sum of the angles, we have to use the formula S equals n minus 2 times 180 degrees, where n is the number of sides of a polygon. So we have to substitute 5 to n since a pentagon has 5 sides. Now we have 5 minus 2 times 180 degrees, which gives us 540 degrees. Then now, to find the size of the angles, we have to use the same formula but divide it by n. And now, since we know that n is equals to 5, so we have to divide 540 degrees by 5, which gives us 108. So that means that each angles of the pentagon has 108 degrees. Next, we have deflection angles. It is an angle in which a survey line makes with the prolongation of the preceding line. It is measured clockwise or counterclockwise from the prolongation of the previous line. Deflection angles are always less than 180 degrees.
Hello everyone, this is Eisha, Genabe, and in this section I'll be talking about bearing and azimuth. So first we define what is bearing. The bearing of a line is the acute horizontal angle between the reference meridian and the line. The direction of the line may be described by giving its bearing. The bearing is measured either from the north or south towards east or west. That would give an angle less than 360 degrees. The angle is represented by N or S for north or south first, followed by the angle value and E or W for east or west direction. So we have two examples here on how bearing is being written. We have the first example, which is north represented by N, then the angle value 30 degrees, then east represented by E. So we have the second example, which is south represented by letter S, then the angle value 120 degrees, then east represented by letter E. There are two types of bearing. When the bearing of a line is observed in the direction in which the survey progresses, it is referred to as forward bearing. On the other hand, if the bearing of the same line is observed in an opposite direction, so it is referred to as back bearing. Here is an illustration for forward and back bearing. So for the line AB, it progresses towards the north on an angle 44 degrees and 38 minutes east, and if we observe the same line in an opposite direction, which we consider as back bearing, it goes south on the same angle, which is 44 degrees and 38 minutes going west. So it is the same with lines BC, CD, and DE. So again, forward bearing is when the bearing of the line is observed in the direction in which the survey progresses, and on the other hand, back bearing is when the same line is observed in an opposite direction. Next, we define what is azimuth. So the azimuth of a line is its direction as given by the angle between the meridian and the line measured in a clockwise direction from either the north or the south branch of the meridian. The same with bearing, there are also two types of azimuth, the forward and back azimuth. So the forward direction of the line is given by the forward azimuth, while the reverse direction of the line is given by the backward azimuth. The forward azimuth is converted into back azimuth by adding or subtracting 180 degrees. Basing on our illustration here, for the azimuth line AB from the south, we have a forward azimuth of 230 degrees, and we can convert this into back azimuth by subtracting 180 degrees, then we get 50 degrees for the back azimuth. And the same goes with lines BC, CD, and DE for the line azimuth from south and from north. Now how do we convert azimuth to bearing? So we have here four quadrants, the northeast quadrant, which covers the angles from 0 to 90 degrees, the southeast quadrant, which covers the angles from 90 to 180 degrees, the southwest quadrant, which covers angles from 180 to 270 degrees, and lastly the northwest quadrant, which covers the angles from 270 to 360 degrees. Now to convert azimuth to bearing, if the given azimuth is located in the northeast quadrant, it stays the same. And if the given azimuth is located in the southeast quadrant, we subtract the azimuth from 180 degrees. If the given azimuth is located in the southwest quadrant, we subtract 180 degrees to the given azimuth, and lastly, if the given azimuth is located in the northwest quadrant, we subtract the given azimuth to 360 degrees. We have here the azimuth to bearing conversion example. So the first given azimuth is 84 degrees. And the first thing we need to do is to locate which quadrant does it belong to. So for 84 degrees, it is located in the northeast quadrant. So the angle value stays the same if we convert it into bearing. That is why we have here north 84 degrees east. So for the second given azimuth, we have here 125 degrees. It is located in the southeast quadrant. So we need to subtract the given azimuth with 180 degrees. So we have here south 55 degrees east. So for the third given azimuth, we have 258 degrees. It is located in the southwest quadrant. So we need to subtract 180 degrees from the given azimuth, which is 258 degrees. That is why we have here south 78 degrees west. And for the last given azimuth, which is 279 degrees, it is located in the northwest quadrant. So we need to subtract the given azimuth, which is 279 degrees, with 360 degrees. That is why the equivalent bearing is north 81 degrees west.
Hello everyone, I am Nichole Padilla and I'll be presenting the types of compasses and its uses. Starting with the Brunton compass, it is described as a fancy, highly precise compass used by geologists, surveyors, engineers, and archaeologists. It is one of the most versatile and widely used compasses as it combines the features of a prismatic compass, sighting compass, hand level, and clinometer. It is used for navigation and also to measure the strike and dip of rock layers in the field. It is suitable and sufficiently accurate for preliminary and exploratory surveys, engineering type surveys, and topographic surveys requiring only low degrees of precision. The Landsat compass, often referred to as the military compass that is made up of three parts: the cover, the base, and the reading lens. It consists of an aluminum case containing a magnetic dial balanced on a pivot, a hinged cover with a sighting wire, a hinged eyepiece containing a magnifying glass for reading the dial graduations, and a sighting slot for viewing the distant object. It is used to figure out your bearing where magnetic azimuths are required. It is also designed for military use, such as in reconnoitering, determining directions, orienting maps, and artillery fire direction control. The surveyor's compass is one of the two main kinds of magnetic compass, the other being the prismatic compass. It is usually the larger and more accurate instrument, and is generally used on a stand or tripod. This is a surveying instrument that determines the horizontal direction of a line with reference to the direction of a magnetic needle. It has a compass box containing a graduated circle, two sight vanes, magnetic needle, and two clamping screws. A glass cover protects the needle and the graduated circle. It is used for measuring horizontal angles and for determining the magnetic bearing of a line of sight. It was popularly used earlier for running limited plane surveys of reasonable accuracy. Now, it is commonly used for forest surveys, in retracting old land surveys, and in geological explorations. The plain pocket compass is a small hand instrument with a magnetic needle enclosed in a non-magnetic case, the needle being free to swing over a graduated face or dial. It is similar to the surveyor's compass, except that it has no sight vanes. It is used for obtaining a rough bearing of a line. It is also used in reconnaissance and exploratory surveys. The prismatic compass is one of the two main kinds of magnetic compasses, the other one being the surveyor's compass. It is a small navigation and surveying instrument held by hand for observing, and is therefore employed on the rougher classes of work. The graduations are found on a rotating card instead of being on the compass box. The card moves with the needle since both are fastened together. Two short sighting devices are provided, and magnetic bearings are read by means of a prism at the same instant that the compass is sighted along the line. It is widely used by sailors for navigation at sea. It is extensively used to find out the bearing of the traversing, including the angles between them, waypoints, and direction. The forester's compass is another type of pocket compass optimized by some in the forestry professions. It is usually made of aluminum or some type of metal, which does not affect the free movement and positioning of the magnetic needle. It is widely used in forestry surveys as well as for geological and other similar exploratory surveys. The transit compass is similar to the surveyor's compass, only it is mounted on the upper plate of the transit. It is used to check horizontal angles and directions measured or laid off during transit surveys. It is also used for orienting the transit with a magnetic meridian. Now let's proceed to the common errors and mistakes in compass work. The first source of error in compass work is a bent needle. When the needle is bent, all observed bearing will have a constant error. Second, bent pivot. The magnitude of the error will depend upon the direction in which the sight is made. Third, plane of sight is not vertical, where the line of sight may be steeply inclined. Fourth, local attraction. This is the phenomena by which the magnetic needle is constantly prevented to point towards the magnetic north at a place. Lastly, errors in reading the needle. This error is due to the inability of the observer to determine exactly the point on the graduated circle where the needle comes to rest. The first source of mistakes in compass work is reading the wrong end of the magnetic needle. Next is not releasing the needle completely and not allowing it to swing freely about the pivot. Lastly is mixing or interchanging the recording of azimuths from north and south, magnetic and true bearings, clockwise and counterclockwise angles, or forward and back bearings.
That is all for our report. We hope that you learned something from it. Thank you for listening.